In this example problem, we're going to design the double T beams from one of our previous examples. Our double Ts are part of this parking structure where the double T frames into an inverted T on one side and an L beam on the other side. The span length is given as 61 feet. Our load is given here. So our live load is from ASCE 7 for a parking structure as 0.04 KSF. And then our superimposed dead load is an approximate value from the PCI Design Handbook, which is 0.005 KSF. We need to assume some initial material properties for the design. So the initial material properties are shown here. And these are typical values that you can start with for a building design. We'll need the modulus of elasticity for several steps in the design, and we can use the equation from ACI 318-19 shown here for normal weight concrete. We'll need the modulus at release using the concrete strength at release and the modulus at ultimate or in service where we use the F prime C. So 5,000 PSI for our 28-day strength or F prime C and 3,500 PSI for our strength at release. Note that in our ACI, we need to put in units as PSI underneath our square root. Our first step is to decide on our preliminary section. And we're going to use the PCI Design Handbook to help with this process. So we're going to assume that we have a 10-foot wide top flange for our double T. And we have our span length of 61 feet and our total superimposed service load of 45 pounds per square feet. So we can come and look at different design tables, and this is the design table for a 10 DT26. So this is a 10-foot wide double T with a 26-inch depth, and we can come to our 61-foot span length, and we want to look at and see where we have a safe superimposed service load greater than the superimposed service load for our section. So you can see here we're kind of right in this range. So 12 strands, 8 is a 1/2-inch diameter, and the last is whether they're straight or depressed. So the straight strands is saying that we could use a 7-inch height from the bottom to the centroid of the strands. D1, we would have larger eccentricity at midspan. So that'll be kind of the starting point for our design, is between the straight strand and depressed strand scenario there. The PCI Design Handbook also has some section properties and other details for the section. So for our section that we chose, we have some details on the geometry, including web thickness and top flange width and thickness. We have our overall height, and then we also have some section properties. We're going to assume that we're using normal weight concrete, so we'll use these properties on the left. And you can see that we have area, moment of inertia, the distance between the bottom and top to the centroid, and our different section moduluses. And then we also have our weight here. So the weight we can use, this is the self-weight of the section in units of pounds per feet, and I convert it here to kips per feet. Our next step is to find our loads and demands for our preliminary section that we chose. We had our self-weight from our design table, but we can also find it based on the area and the density of the concrete. So if we assume a density of 0.15 kips per cubic foot and the area as given in the design table, we can calculate a distributed self-weight. So you can see that this is the same value that we had from the design table on the previous slide. We can next look at our distributed superimposed dead load and our live load. And to do that, we need a tributary width. We're going to assume that the beams are placed side by side. So the tributary width for each beam is equal to the width of the top flange, which is 10 feet. So to find our distributed superimposed dead load, we'll take our surface load times 10 feet, which will give us our distributed load here, 0.05 kips per foot. We can add that to our self-weight to get the total distributed dead load of 0.768 kips per foot. We can then find our distributed live load by taking our surface load times 10 feet to get 0.4 kips per foot. Our service load we can find by just taking the dead load plus the live load, so no load factors when we're talking about service. And we'll get a total service load as shown, 1.168 kips per foot. And when we're finding our factor distributed load or our ultimate load, we'll include our load factors from ACI. So our 1.2 times dead load and our 1.6 times live load. And that'll give us our total ultimate load of 1.561 kips per foot. We're going to need the moment and the shear along the length of the beam for our design. So we can use these equations just for simply supported beam to find the moment and the shear along the length of the beam, where x is the distance between the left support and the point of interest. We can plot these two equations along the length of the beam at different sections and with different loads, and that's what I'm doing here in these tables. You can see the x value is the distance from the left edge. We're only showing half of the beam because the beam response will be symmetrical. And you can see I'm highlighting a couple different points of interest, h over 2, which is important for shear, the transfer length, and the development length. The transfer length and development length we'll find later in the calculations, and I just come back and I input those manually into these two fields. So you can see we're finding the self-weight, the weight of any topping. We don't have any topping because it's a pre-top section. The superimposed dead load and live load up here. And then some of the loads that we'll need for our design, we'll need our response at release. We'll need our service loads, and we'll also need our ultimate loads. So I include those here in this table. We're now ready to move into the design phase. So first we can choose the cross section. We did this already and we found that we'll use a 10 DT 26 pre-topped double T section with a 10-foot top flange. Next, we need to choose the amount of pre-stressing. From the PCI Design Handbook table, we saw that we could probably start with 12 half-inch diameter strands. I'm going to give us another procedure to calculate how many strands to start with, or approximate how many strands we want to start with. So we'll go through that here. So this is a starting point based on a current point analysis. And for this, we need to approximate our E plus KT value. So we'll come to the table that I'm showing here on the right. We have a double T section and we need E plus KT, which is going to be 0.7 times H. So 0.7 times the height of our section, 26 inches, is going to give us an E plus KT of 18.2 inches. So next we need to calculate the tensile stress limit at service. So at service, we're going to assume that we have a class U beam, an uncracked beam. So we can find our tensile strength equal to 7.5 times the square root of F prime C. Again, we enter in our F prime C in terms of PSI, and then we'll find our tensile strength to be 0.53 KSI. Some of the other values that we'll need for our current point equation are the stress and the pre-stressing after all losses. We're going to assume 15% losses, so that's why we're using a 0.85 there. And the 202.5 is 75% of the ultimate strength for our strands, a typical value for initial stressing of the strands. And then our maximum moment is our maximum service moment from the tables that we're looking at on the previous slides. So next we can plug these values into our current point equation. And our current point equation here will help to ensure that we meet our stress limits at a certain point. So here we're looking at midspan and we're looking at the bottom fiber stress limits. So we can plug in our values. We have our maximum moment, which is 6,518 kip inches, minus our S sub B for our section. So I found that up here for you, is 1,514 inches to the third. Our tension stress limit, 0.53 KSI. And then this is all divided by our E plus KT, 18.2 inches times F sub PE, 172.1 KSI. So we'll get that our area of our pre-stressing should be greater than or equal to 1.82 square inches. So we can next choose the number of, or the size of our strands and the number of strands. And we can see that if we use 12 half-inch diameter strands, we'll get an area that's just greater than that value. So that's where we're going to start, is 12 half-inch diameter strands. Next, we can choose our tendon profile and decide whether we need strand debonding or harping. And we're going to use our current point analysis again and current point equations to find the maximum and minimum eccentricities at the end and the maximum and minimum eccentricities at midspan. So we can start with our maximum and minimum eccentricities at the ends. So starting with the maximum, we need to find the allowable tensile stress here. And in the end region at release, we have the stress limit is 6 times the square root of the release concrete strength. So we find that there. Our bottom current point we can find based on our section modulus to the top and our gross area. And we can estimate the strand stress after elastic shortening. We're going to assume that we have about 6% or 10 KSI elastic shortening. So 6% losses takes us down to the value here, 190.4 KSI. So next we can take that value times our area of our 12 strands. So the area of our 12 strands is 1.836 square inches times the stress 190.4 KSI to give us a total force here of 349.5 kips. So if we had debonding, we would reduce the area of that pre-stressing in this equation. Next, we need the moment at the ends of the beam. We're going to assume that we're right at the end, so we're not going to have any moment here. But if we were at midspan or so, then our minimum moment at this point is going to be the self-weight moment, because these are our stresses at release. So we can plug these values into our current point equation for our maximum eccentricity. So we'll have 7.8 inches plus our minimum moment, 0 kip inches, plus our section modulus, which is 5,379 inches to the third. Our stress limit here is 0.35 KSI, and we're going to divide by our initial pre-stressing force after elastic shortening, 349.5 kips. So we'll get our maximum eccentricity here to be 13.3 inches. We can do a similar process to calculate our minimum eccentricity at the ends. The minimum eccentricity at the ends is going to be based on our service state. So the service tension limit we found before, at service, we have to include all losses. So we're going to assume 15% losses again. Use that with our 12 strands to calculate the total force in the strands. And at the ends, we still have no moment. Our top current point, we can use the equation shown here based on the bottom section modulus and the gross area. And then we can plug these values into our minimum eccentricity equation. So here we'll have our moment 0 kip inches minus our section modulus to the bottom 1,514 inches to the third times the tensile strength or the tensile stress limit 0.53 KSI. Divide all this by 316 kips and then subtract off our K sub T 2.2 inches. So that'll give us a minimum eccentricity of negative 4.7 inches. So we can see then we have our minimum eccentricity and our maximum eccentricity, and we can do the same thing to find the minimum and maximum eccentricity at the midspan. So we would change our stress limits to the midspan limits and change our moments to the midspan moments, minimum including just self-weight and maximum including all of our service loads as well. So we can then have a range of eccentricities that would be designed to meet the stress limits at midspan and at the ends. And if we can have a straight strand profile within this region, then we know we're good and we can have a straight strands in the beams. Here you can see there aren't any, there isn't any eccentricity that would meet both midspan and end. So we would likely need to either harp or debond strands. I'd also note that a negative eccentricity would be at where the strands are above the centroid of the section. So positive would be an eccentricity below the centroid of the section, and negative would be above. We're going to try moving forward with an eccentricity around 15 inches, and we'll see where we meet our stresses and where we don't. We're now ready to choose the actual location of the strands. So we know we have 12 strands. We know an approximate eccentricity that we want to place the strands at, but every section is going to have a possible or a grid of possible strand locations. So typically pre-stressing strands are going to be on a 2-inch by 2-inch grid, and with a double T section, typically you'll be able to have 2 strands next to each other in each layer in each web. So you can have a total of 4 strands per web, per layer across both webs. So we're going to start, or we can play around with this. We're going to start assuming that we have a strand pattern as shown here. So I have a different table where we can have a different strand pattern at the center line and the ends with a different height of the strands. So just by adjusting the height of each layer, we can change that. So we have 2 layers in two strands in our bottom layer, then 4 strands in the next layer up, then 4 strands, and then 2 strands. So just to kind of show you where these, the centroid of the strands come from, they come from a weighted average. So we can find our YP by taking, we have 2 strands in the bottom layer, which is 2 inches from the bottom. Then we have 4 strands in our next layer, which is 4 inches from the bottom. Then we have 4 strands in the next layer up, which is 6 inches from the bottom, and 2 strands in our final layer, which is 8 inches from the bottom. We divide this by our 12 total strands, and that gives us the centroid of 5 inches, which is the same one that I found in the table. So this is just what's happening in that table up there. So we can find our eccentricity then by taking our distance between the centroid and the bottom, YB, minus that YP, which is the distance between the bottom and the centroid of the strands, to give us our eccentricity. And again, we were shooting for right around 15 inches, so we're at 15.29, so that's close enough. At this point, we're ready to move from the design process to the analysis process for our section, in terms of the flexure design at least. So we have a 10 DT26 with given properties, and we have 12 half-inch strands giving us this area, and our grid gives us a YP equal to 5 inches. And here are our material properties from the beginning again. So we're going to continue to move forward with these. So now we're going to analyze this section. During the design procedure, we assumed a prestressed loss, but now we need to calculate the actual prestressed losses based on the actual number of strands we have and the location of those strands. So we can start by calculating our jacking force. And this is the force in the strands before elastic shortening happens. So our jacking stress here, 0.75 times the ultimate stress, or 202.5 KSI, times the area of our strands will give us a force here of 371.8 kips. Then we can plug this into our equations. We're using the procedure from the PCI Design Handbook. So we can first find the stress in the concrete at the centroid of the pre-stressing strands. So our F sub CIR is going to be equal to 0.9, which is our value for pre-tension members, times 371.8 kips divided by 689 square inches plus 371.8 times our eccentricity, 15.3 inches squared, divided by our gross moment of inertia, 30,716 inches to the fourth. And then we have minus our self-weight moment, 4,006 kip inches. Our eccentricity, 15.3 inches, divided by 30,716 inches to the fourth. So we'll get our FCIR equal to 1.038 KSI. We can take that and plug that into our elastic shortening equation. So again, we have a K sub ES equal to 1.0 for pretension members, times 28,500, the modulus for our pre-stressing divided by our release modulus, so 3,372 KSI, times our FCIR 1.038 KSI will give us elastic shortening losses equal to 8.8 KSI. So next we can find all of our long-term losses, and we're going to start by finding our creep. And for our creep, we need to include our stress due to the superimposed dead loads. So for this, our M sub SD, so our moment due to superimposed dead loads at midspan, is equal to 279 kip inches. Our eccentricity we still have as 15.3 inches, divided by our moment of inertia here, 30,716 inches to the fourth, will give us a stress equal to 0.139 KSI. We can plug this stress into our creep loss equation, assuming that we have a normal weight concrete. So we'll get 2 times, here you can see we're using the modulus of our pre-stressing, 28,500, divided by the modulus of our ultimate strength, so our final concrete, so 4,031 KSI. And then this is then times our 1.038 minus 0.139. And we'll get a creep loss here equal to 12.7 KSI. So we have our creep and our elastic shortening loss. Next, we can find our shrinkage loss. And to find our shrinkage loss, we'll need our volume to surface area ratio. So this is a value that's given in the PCI Design Handbook. And for our section, we have that equal to 2.05 inches. Our relative humidity, this is based on the location of the building and whether it's an interior or exterior exposure. So here we have a relative humidity equal to 70%. Our shrinkage factor, which is 1.0 for pre-tensioned components. And then we can plug all these values into our shrinkage loss equation. So using our shrinkage loss equation, we'll have 8.2 times 10 to the negative 6 times 1.0, our shrinkage factor for pre-tension components. Our modulus for our steel, 1 minus 0.06 times 2.05 inches. And then 100 minus 70, where our 70 is we enter in 70 for 70%. So we'll get a value here of 6.1 KSI. So that's our shrinkage loss for our section. Next, we need to find our relaxation loss, and to do this, we're going to need to use the tables here from the PCI Design Handbook. We have grade 270 low relaxation strands. These are typical. So with that, we have a K relaxation of 5,000 PSI or 5 KSI and a J equal to 0.04. We can find the ratio of our jacking stress to ultimate, which again will typically be 75% or 0.75. And coming here in the table for low relaxation strands, 75%, we can see we have a C equal to 1.0. We can use these values that we found in the table with our losses that we calculated before to calculate our relaxation loss. So we can see we'll have a relaxation loss here of 3.9 KSI. Then we can add together all of our four components, our elastic shortening, creep, shrinkage, and strand relaxation losses to get our total loss of 31.5 KSI. Next, we can calculate the pre-stressing stress and the force for our stress calculations. And the two main forces that we'll need are the stress and force after transfer, so just after elastic shortening, and the stress and force at service, including the total losses. So to start, our stresses after transfer are going to be our 202.5 minus our elastic shortening loss, 8.8 KSI, which will give us a final stress in the strand here of 193.7 KSI. Then we need to take that stress, 193.7, times the area of our pre-stressing. Our 12 half-inch diameter strands will be 1.836 square inches. And that'll give us a force here of 355.7 kips. So here we have the force that we'll use when we're looking at release, and we have the force that we'll use when we're looking at service. So note that these values were all found based on a specific concrete strength and specific section properties. If anything about our design changes, then we need to go back and recalculate our pre-stress losses. So just make a note of that. Our next step is to check the concrete stresses using the actual stress in the pre-stressing strands that we found on the previous slide. Note that we're going to use the force in the tendon approach with gross section properties, and note our sign convention is going to be positive for compression and negative for tension. We'll use the concrete stress limits from ACI 318-19, and I summarize those in these two tables. So our stress limits at release, our compressive and tensile stress limits at the ends of the simply supported member and at all other locations are summarized in the table for a concrete strength of 3.5 KSI or 3,500 PSI. Our stress limits at service are summarized here. We have our compressive and tensile stress limits due to our sustained loads and due to our total loads. So you can see we need to meet all of the stress limits that are summarized here. Next, we're going to calculate our actual stresses, and we'll start with our stresses at release. So here are our general top fiber stress and general bottom fiber stress equations. You can see we're just using P over A, our axial stresses, plus My over I, our flexural stresses for the stress caused by the strand eccentricity and stress caused by any external moment. So we can start with our stresses at release, and we can calculate our top fiber stresses. So here we'll have 355.7 kips divided by our gross area, 689 inches squared, minus 355.7 kips times our strand eccentricity, 15.3 inches, times the distance between the centroid and the top of the section, which will be 5.71 inches. And then all this divided by our gross moment of inertia, 30,716 inches to the fourth. We add back in our moment here. Our self-weight moment is going to cause compression in the top fiber, so we have a positive sign. And our moment is going to be 568.8 kip inches times YT 5.71 divided by moment of inertia 30,716 inches to the fourth. So we'll get our stress here, FCT, equal to negative 0.39 KSI. So this is the stress in our the stress in our top fiber at the transfer length. So the moment here is at the transfer length. And we have a tensile stress. So we can compare this to the tensile stress limit at the end region, 6 times the square root of F prime CI. And we can see that the actual stress is greater than the limit, so we're no good. We don't meet this initial check. Next, we can check the stress at the bottom. So our axial stress term is going to be the same. 355.7 kips divided by 689 inches squared. We're adding the eccentricity is going to add compression here. So 355.7 kips times our eccentricity 15.3 inches times the distance between the centroid and the bottom of the section, 20.29 inches, divided by 30,716 inches to the fourth, minus, so our moment's going to cause tension in the bottom, 568.8 kip inches times 20.29 divided by 30,716 inches to the fourth. And we're going to get our bottom fiber stress here then equal to 3.735 KSI. So we can see this is greater than our compressive stress limit of 2.45, so we're no good here as well. So our stresses don't check at the end region. And our stresses need to check along the whole length, so we can check that, which we'll do on the next slide. But typically at release, our stresses are going to control at the end region. Here we have our stresses along the length of the beam compared to the tension and compression limits. And you can see we don't meet our compression check at several different places, or a distance along the length of the beam. And we don't meet our tension checks at the end. If we increase our concrete release strength to 6 KSI and increase our ultimate strength to 8 KSI, we're going to get that, we're going to find that our stresses check along the length. So this is the simplest fix at this point in terms of calculations. In actuality, it might be better to go back and try to debond some strands or harp some strands, since our end region stresses are the ones that don't check. But we're just going to move forward by increasing the compressive strength in this example. Next, we need to look at our stresses from our sustained loads. Here are general top fiber and bottom fiber stresses from our sustained loads. And note that when we're talking about sustained loads, we're going to use the pre-stressing force at final or at service. So taking out all of our pre-stress losses. So you can see a piece of F and a piece of F here. So our top and bottom fiber stresses with our sustained loads, which are our self-weight and our superimposed dead load. So again, we're looking at the transfer length in this example. So the superimposed dead load moment at transfer is shown here. And then our total sustained load moment at transfer length is just the sum of the self-weight moment and the superimposed dead load moments. So that's given here. The pre-stressing force is going to be the final pre-stress force. And remember, we changed the concrete strength on the last slide, so we would need to go back and recalculate all of our pre-stress losses. So I did that already. I'm not showing that on these slides, but the new pre-stress loss would give a final stress in the strand equal to 175.5 KSI. So we use that new value with our area of our 12 half-inch diameter strands to get our total pre-stress force at final or at service of 322.2 kips. We use that value in our equations with our moment, and we can find a top and bottom fiber stress as shown here. See, we still have tension in the top and compression in the bottom. And we can see that the compression stress limit due to sustained loads, which is 0.45 times F prime C, is greater than the compression that we have in the bottom fiber. So we meet our checks here. And if we check along the length of the beam, we can see that we have the maximum compression right at our transfer length, and we're under the sustained load compression stress limit. Our final stress check is going to be the stress check for our stresses from all of our service loads. So we have, again, our general top fiber and bottom fiber stress checks. Again, we have our P sub F, our final force in the pre-stressing strands. So we can use the same one we found on the previous slide with our recalculated losses. And you can see now we'll have all of the moment applied to the beam at service, so including our live load moments. So plugging in the different values, we can find the top fiber stress at midspan, and we can check this stress versus the limit and see that we're okay here. So we have compression in the top and it's less than our limit, so that's okay. And then again, checking the bottom fiber at midspan, we can find we'll have tension in the bottom fiber at midspan, but this value, a tensile stress of negative 0.583 KSI is less than the tensile stress limit, 7.5 times the square root of F prime C, which is 0.67 KSI. So we can check these along the length, and we can see that compression remains under the limit, and our tensile stress is just under the limit here at midspan. So all of our stresses check. We can now move on and check the flexural capacity of our section. And our design objective here is to make sure that phi mn is greater than or equal to mu along the length of the beam. We're going to use the rectangular stress block approach and equilibrium, similar to what we do in a typical reinforced concrete design. The one difference is that we'll need to calculate a stress in the strand using this equation here from ACI. There are other procedures to find the strength, the flexural strength in pre-stressed concrete members, but what I'm showing is the simplest. So our first step here is to find the rectangular stress block coefficient beta 1, and we have 8 KSI concrete, so beta 1 is going to equal 0.85 minus 0.05 times 8 minus 4, which will be equal to 0.65. This is greater than or equal to 0.65, so this is the value that we'll use for beta 1. Next, we can find the depth of our pre-stressing. So here we have the height of our section, 26 inches, minus our YP, 5 inches. So the depth of our pre-stressing is going to be 21 inches. We can next find our pre-stressing ratio. And our pre-stressing ratio is our total area of our pre-stressing strands, 1.836, divided by the width of our compression region. So our compression region width is 10 feet. So the width of the top flange, 10 feet or 120 inches, times d sub p, which is 21 inches. So our rho here is going to be 0.00073. So next we can plug this value in and find the strand stress at ultimate using the equation here from ACI 31819. So we'll have 270 KSI times 1 minus 0.28, our gamma sub p factor, 0.65, our rho sub p 0.00073, and then 270, our ultimate strength of the strand divided by 8 KSI, the strength of our concrete. So we'll get an F sub PS of 267.1 KSI. So this would be the assumed stress in the strand when our section fails. Using the stress diagram and setting tension equal to compression, we can find the tension from our pre-stressing equal to the compression from our rectangular stress block region. We can solve for A and find the depth of the compression block. So we have the area of our pre-stressing 1.836. We have the stress in our strands 267.1 KSI. And we're going to divide by 0.85 times 8 KSI concrete. And B, we're assuming that the compression block stays in that top flange, so we'll have a width of 120 inches. So then we'll have a value here of 0.6 inches. We can compare this to the thickness of our top flange. So the thickness of our top flange is equal to 4 inches. So our compression block remains in the top flange, which means we can move forward with these calculations. So our neutral axis depth then we can find by just taking A 0.6 divided by beta 1.65. So we'll get a C equal to 0.92 inches. And we can use that to find the strain in the pre-stressing at the centroid of the pre-stressing strands. So for that, we'll assume that we have a top fiber strain of 0.003. We'll assume a linear strain distribution, plane sections remain plane, and we can solve for the strain in the centroid using this equation here. So we'll find the strain is equal to 0.0651, which is greater than our tension controlled limit of 0.005. So our section's tension controlled, so we can use a phi factor of 0.9. So next we need to find our flexural strength, and to do that we'll sum our moment about the centroid of our compression block. So the force that we'll have is our area of our pre-stressing strands, so 1.836 times 267.1 KSI, the stress in our strands, times the depth of our pre-stressing strands, 21 inches, minus A over 2, 0.6 inches divided by 2. And this will give us a moment here of 10,152 kip inches. We can take that times 0.9 to give us our phi mn, and then we can compare that phi mn to our mu. Here you can see phi mn is greater than mu, so at midspan we meet our design objective. We can calculate how much excessive strength we have using the safety index. So just dividing phi mn divided by mu, we can see we have a 5% greater strength than we need, which it is okay. The stresses and the flexural capacity should be checked along the length of the beam, and we want to include the transfer length and development length in those calculations. The transfer length is the length required to transfer the pre-stressed stress in from the strand to the concrete. So at a distance LT, you're going to have a stress in the strand equal to F sub SE, the service stress in the strand. The development length goes from the start of bonding for the strand to the point where we can get the ultimate stress in the strand at flexural failure, F sub PS. So at this point and at this point, you will have the full service stress in the strand and the full ultimate stress in the strand. So to find these, we can use the equations from ACI 318 as shown here. And the first one we'll have is F sub SE over 3,000. So 175,500 PSI divided by 3,000 times the diameter of our strand, 0.5 inches, will give us a transfer length of 29.3 inches. We can then use the development length equation here. So the first term is just our transfer length, so 29.3 plus 267,100 psi minus 175,500 psi divided by 1,000 times 0.5, which will give us a value here of 75.1 inches. So here's our transfer length and our development length, which we can use in these equations shown here. At midspan, our available development length is half of our beam length, which will be 372 inches. And we can see that this is much longer than the required development length of 75.1 inches. So we can plot our moment along the length of the beam, our capacity along the length of the beam, and compare it to our demand along the length. And we can see that we have sufficient capacity, or our factor resistance is greater than our demand along the whole length of the beam. So the beam has sufficient flexural capacity. Next, we can check the minimum flexural reinforcement requirement. So this requirement says that our factored nominal capacity needs to be greater than or equal to 1.2 times the cracking moment strength. And this is essentially a ductility requirement, ensuring that our beam doesn't crack and then immediately fail. We want our beam to crack and then have some excess capacity so that the cracks give us warning that a beam is nearing failure. So that's a built-in safety factor here. So we have the following equation from the PCI Design Handbook that we can use here for cracking moment. And this equation is essentially derived from setting our bottom fiber stress at midspan equal to the tensile strength of the concrete. So here we have an S sub BC, which is the section modulus for the composite section compared to the gross section. So we don't have a cast in place composite deck, so our S sub B is equal to S sub BC. So that'll be equal to 1,514 inches to the third, and this second term here is going to be equal to 0. The rupture strength of the concrete is just 7.5 times the square root of F prime C. And then the pre-stress force at service we can find is just the area of our pre-stressing times the stress in our strands at service after all of our losses. So plugging in our different values for M sub CR, we can find M sub CR equal to 1,514 inches to the third times 0.671 KSI plus 322.2 kips divided by 689 square inches plus 322.2 times 15.3 divided by 1,514 inches to the third. So we'll get a cracking moment here of 6,650 kip inches. We can compare, or we can take 1.2 times 6,650 and compare it to our nominal moment, 9,137, and see that we have sufficient reinforcement to meet our minimum flexural reinforcement requirement. Our next step is to check our deflections, and we're going to check our deflections using the PCI multiplier approach from the PCI Design Handbook. With this approach, we'll calculate 4 base deflections, and then we can use different multipliers to find the total deflection at release, at time of erection, and at final time. So we'll need to check the we're going to assume that our structure does not support any non-structural elements likely to be damaged by large deflections. And because we're making that assumption, we're going to check our immediate deflection from live load. So our live load deflection needs to be less than L/360. And we also need to check to make sure that the deflection after the attachment of non-structural elements is less than L/240. And this deflection is going to be equal to the deflection shown here. So to calculate our deflections, we need our release modulus and our final modulus. We changed our concrete strength, so I'm recalculating those values here. So we'll use these to find our deflections. We'll now calculate all the deflections that were in blue in the previous table. So our first deflection is our deflection from pre-stressing for straight strands. So we have the deflection as negative, our strand force 359.5 kips. This is our initial pre-stressing force in the strands, and then times our eccentricity, 15.3 inches, and then take this times our length. So we have our 61-foot span length, and we need to convert that into inches. And then this is squared. And then this is all divided by 8 times our release modulus, 4,415 KSI, times our gross moment of inertia, 30,716 inches to the fourth. So we'll get the deflection from pre-stressing to be 2.71 inches. And we're going to have an upward, that'll be an upward deflection. So next we need to find our deflection due to self-weight. And notice that I converted our units to kips per inch so that have consistent units throughout. So here we'll have our deflection due to self-weight equal to 5 times 0.0598 kips per inch times our length. So again, we need to do 61 feet times 12 inches per foot. This is all to the fourth, or the length at L to the fourth, and then divided by 384 times our modulus, 4,415 KSI. So our release modulus, and then times our gross moment of inertia, 30,716 inches to the fourth. So we'll get a deflection here of 1.65 inches. And again, our direction here from our self-weight is going to be down. So we can do the same thing with our superimposed dead load. So just same equation, except change the distributed load here. And then also note, when we're looking at our superimposed dead load, we're going to use EC rather than ECI. So our modulus assuming the final concrete strength. So we can calculate that deflection as 0.1 inches down. And then our deflection from our live load, we have our distributed live load. And again, we're going to use the stiffness of our concrete or modulus at service. So again, 5,098 KSI. So that'll give us a final deflection of 0.8 inches downward. So these are the 4 main deflections that we'll need with the PCI multiplier approach. We can use the PCI multiplier equations with the deflections we found on the previous slide to calculate the deflection at time of erection and the deflection at final time. So the deflection at the time of erection is going to be equal to 1.8 times our deflection due to pre-stressing, 2.71 inches, minus 1.85 times our deflection due to self-weight, 1.65 inches, minus our deflection from our superimposed dead load, 0.1 inches. So we'll get that to be equal to 1.73 inches. The final camber, we can plug in our values into those equations. So 2.45 times our initial pre-stressing force, or sorry, initial pre-stressing deflection, so 2.5 times 2.71 minus 2.7 multiplier for our self-weight, so 2.7 times 1.65 inches, and then minus 3 times the deflection from our superimposed dead load, so 3 times 0.1 inches. And that'll give us a final camber of 1.9 inches. And these are both upward deflections. So now we have all the values that we need to check our different deflection limits. First, we need to check the deflection from live load only. So the live load deflection we found to be 0.8 inches, and that needs to be less than L over 360, which is 2.0 inches or 2.03 inches. So that check is okay. Next, we need to check the deflection after the attachment of all of our non-structural elements. So we can plug in our values from from the equation here from PCI and see if it's, those values, plugging them in, we'll get a deflection of 0.63 inches. And this is less than L over 240, which is 3.05 inches. So our section meets the different deflection checks. For the last part of the design, we need to check shear and design for shear. Our general design requirement for shear is shown here. So phi sub v times vn needs to be greater than or equal to v sub u. Our v sub n is made up of a concrete and shear component, so v sub c plus v sub s, and our resistance factor is going to be equal to 0.75. There's an upper limit on the shear resistance as shown here, and this upper limit just makes sure that our concrete in our diagonal struts doesn't crush before we have the yielding of our vertical shear reinforcement. So next I show the depth, or how to find D based on ACI. So the D that we can use in our shear equation can be the max of our actual strand depth, D sub P, and 0.8 times H. So here the max of those two is actually going to be D sub P, so that's the value that we'll use in our equations. Finally, our critical section, we need to find the location of the critical section. So we're assuming that the distance from the center of the bearing to the edge of the bearing is going to be 6 inches. So we're assuming a 12-inch bearing. So our critical section is just going to be 6 inches plus H over 2. So the critical section is H over 2 away from the face of the support, so which would be the edge of the bearing in this case. So doing that, we'll find an X critical equal to 19 inches. And with that, we can find the shear and moment at that location. So we're going to use these values, a shear at the critical section of 45.1 kips, and a moment at the critical section equal to 881 kip inches. We'll use those values in the following equations. Finally, we need to decide what our web width is. We have two webs with a tapered width, and we're going to use the 2 times the average width of the web to find our BW. So doing that, we'll find a web width of 9.5 inches. We can now plug in all of our known values into our equations from ACI 318.19. And we're going to use the simplified procedure. So the simplified procedure, we take the minimum of these 3 V sub C values and make sure it's greater than or equal to this value here, 2 times the square root of F prime C BWD, and then that'll be our VC. So plugging in our numbers, we'll have V sub C, or the first component here to be 0.6 times 1.0, our lambda. So we're assuming that we have normal weight concrete, so our lambda is going to be equal to 1.0, times the square root of 8,000 psi plus 700 times 45.1 kips times 21 inches divided by 881 kip inches. And then this will all be times 9.5 inches, our web width, times 21 inches, and then I'm going to convert our units into kips. So divide by 1,000 pounds per kip. And we'll get a value here of 160.9 kips. Our second equation here will have 0.6 times 1.0 times the square root of 8,000 psi plus 700, and then again times 9.5 times 21 divided by 1,000 pounds per kip. So we'll get a value here of 150.4 kips. The final component here, C, is going to be 5 times 1.0 times the square root of 8,000 divided by 1,000, and then times 9.5 times 21. And that'll give us a value here of 89.2 kips. So we can see that 89.2 is going to be the minimum of these three values. So our VC is equal to 89.2, and 89.2 is greater than our minimum VC, which is 35.7. So our VC moving forward will be 89.2. We need to check to see if we can develop our strands at this point. If we can't develop our strands, then we need to reduce this V sub C. But we can see that our available development length is actually equal to our required development length, so we're okay here. We will need to design for shear reinforcement wherever phi times V sub C is less than V sub U. So at the critical section, our phi times V sub C is equal to 66.9 kips, which is greater than V sub U, 45.1. But if we move a little bit away from the critical section, we can see that our phi VC drops below V sub U. So in this region, we would need to provide shear reinforcement for strength. We also need to provide minimum shear reinforcement wherever our phi times V sub C is less than or equal to, or is less than 2 times V sub U. So we have a large portion here where we at least need to provide minimum shear reinforcement. So we're going to see that you can see that phi times V sub C is close to V sub U in this region. So we're going to see if providing the minimum shear reinforcement is going to provide the sufficient strength that we need in that region. We can use our equations from ACI 318 table 9634 to find our minimum shear reinforcement required for our pre-stressed section. So plugging in some of our known values into these equations, we can solve for these. So we'll have 0.75 times the square root of 8,000 psi times 9.5 inches divided by 60,000 psi times, we're going to assume that we have a 12-inch spacing. So we're going to find the amount of steel required per foot, and then we can use that to figure out what actual steel we need to provide. So plugging in 12 inches, we'll find a value here of, sorry, and this is 12 inches per foot. So we'll have a value here of 0.127, and this is the steel that we're going to need, or the shear reinforcement that we'll need per foot. Plugging in our values to our next equation here, we'll have 50 times 9.5 divided by 60,000 psi times, again, 12 inches per foot will give us a value here of 0.095 square inches per foot. And then the last equation here will have the area of our pre-stressing, 1.836 square inches times 270 KSI, or sorry, 270,000 PSI divided by 80 times 60,000 PSI times D, 21 inches, times the square root of 21 divided by 9.5, and then times 12 inches per foot, which will give us a value here of 0.088 square inches per foot. So for our minimum shear reinforcement, we need the maximum of C and D. So the maximum of those two is going to be 0.127, and then the minimum of that value and 0.088, which will be 0.088. So our minimum shear reinforcement required is going to be 0.088 inches squared per foot. We'll continue by looking at the maximum spacing requirements, which we can find in the table shown here. The maximum spacing requirements are dependent on the required V sub S. So we need to compare the required V sub S to the limits shown here. So the limit is just 4 times the square root of F prime C BWD. So we'll find the limit to be 71.4. And the required shear reinforcement at the location where we need the most shear reinforcement is found here to be 3.6 kips. This is less than 71.4, so we can work in the top space here. So our maximum spacing along the length of the beam is going to be 3h divided by 4, 19.5, and the minimum of 3h divided by 4 and 24 inches, which will be 19.5. We can now decide, we know the minimum amount of shear reinforcement required per foot and the maximum spacing. So we can try different combinations of bar size and spacing to get close to the required amount. In precast and prestressed concrete applications, something called welded wire reinforcement or welded wire mesh is often used because it's simpler to place and can speed up fabrication. So here's a picture of the welded wire mesh, and we're going to try using welded wire reinforcement with W 2.9 in each web, and this has a vertical wire spacing of 6 inches. So we have one layer in each web, so we can take 2 times the area of each wire to get the total area here, 0.058 square inches. And then we can take our AV divided by our spacing to get the area per foot. So we can see here that we're providing this area per foot, which is greater than our required area. So using welded wire reinforcement W 2.9 with a 6-inch spacing in each web will meet the shear requirements. Now that we have our shear reinforcement, we need to check to make sure that our design requirement checks along the entire length. And to do that, we'll need to calculate the shear reinforcement contribution to the shear strength. So we can plug in our known values to find our VS. We know our AV here is going to be equal to 0.058 square inches. Our FY is 60 KSI. Our D is 21 inches, and our spacing is 6 inches. So we have a V sub S equal to 12.2 kips. We can plug in that 12.2 into our VN, so add that 12.2 to our VC to get our total shear strength of 101.4 kips. And then we'll factor it, so take that times 0.75 and compare that to our V sub U. So we can see that our phi times V sub N equal to 76 kips is greater than our V sub U equal to 45.1 kips. We can check this along the entire length, and we can see here that our factored shear resistance is greater than our shear demand. So there is sufficient capacity along the length of the beam. and we also meet our minimum shear reinforcement and spacing requirements. The last component that we need to check for shear is we need to make sure that our shear demand is less than the upper limit for our shear strength. So we can compare this at the critical section, and we can see that our shear demand, 45.1 kips, is less than or equal to the upper limit, which we would find to be 174. And if we check the upper limit along the length, we can see that along the entire length, the upper limit is above the maximum demands. So in summary, in this example, we went through and we determined our loads and our shear and our moment to use in the beam design. We chose an initial cross-section and found the number of strands using the PCI Design manual and also the kern point analysis. We selected a strand pattern and strand locations based on the kern point analysis. We decided on the following section. So a 10 DT26 with 12 half-inch diameter strands. And then we checked the design for, we checked the flexural stresses, we checked our flexural strength, we checked the minimum flexural reinforcement requirements, we checked our deflections, and then finally we checked we designed for shear and then checked our shear design. So that concludes this design example.